Welcome to this explainer. Today we're going to try and decode D-Wave's massive technological pivot. We're talking about a real tension here between their immediate financial realities and their, quite frankly, mind-bending long-term roadmap. D-Wave is such a fascinating company to watch right now because they're basically living in two completely different timelines. On one hand, they're dealing with the harsh realities of quarterly earnings reports today, and on the other, they're literally trying to architect the future of computing for the next decade. Let's just rip the Band-Aid off and start with the stark financial hook. Looking at their recent Q1 earnings, they had a massive 81% revenue drop, down to just $2.9 million. Now that number is tough on its own, for sure, but it's set against a staggering $32 million quarterly cash burn. When you see a company burning cash at over 10 times the revenue, well, it immediately begs the question, right? Is this a sinking ship, or is this just the necessary cost of building revolutionary tech? But hold on a second. Before the critics jump in and call the whole quantum sector just a bunch of hype, you really have to look at D-Wave's commercial footprint. It proves their annealing tech is actively being used by major global enterprises today. Actually, they're the very first commercial quantum computing company. We're talking over 135 total customers, with more than 70 active commercial ones. And these aren't just little research labs. This includes over 24 Forbes Global 2000 companies. Right now, D-Wave is literally the only player delivering these optimization solutions at a true enterprise scale. So, to figure out if this revenue crash is a trap or a brilliant long-term play, we really need to dig into the science. Here's exactly how we're going to break it all down. First, the quantum revenue reality, then annealing versus gate model systems, the fault tolerance challenge, an explanation of dual rail qubits, the roadmap to 2032, and finally, balancing today against tomorrow. All right, Section 1, the quantum revenue reality, weighing the financial leap of faith. What's super fascinating here is how perfectly the arguments capture the immense leap of faith investors are taking. On the bear side, you've got that scary $32 million quarterly burn. Critics will argue the quantum sector is mostly just pilot programs right now, and there's a real fear D-Wave might just get leapfrogged by heavyweights like IBM or Google. But the bull case offers a really sharp counter to that. Supporters argue that the 81% revenue drop, it's largely a timing issue or just an accounting artifact. They point out D-Wave's massive head start in optimization, highlighting that they are the only company with real production-grade applications running for enterprise customers today. Moving on to Section 2, annealing versus gate model, a tale of two technologies. This whole financial tug-of-war completely mirrors their technology stack. The core dilemma really boils down to this. You have quantum annealing, which is what actually generates D-Wave's revenue today. It's a niche technology, sure, but it is fantastic for specific optimization solutions. Think routing logistics or scheduling, and it delivers at enterprise scale right now. On the other hand, you have gate model quantum computing. This is the holy grail, the universal computing approach that IBM and Google are chasing, the one that can run complex chemistry and AI algorithms. It's D-Wave's future roadmap, but to get there, you have to solve a massive physics problem. You have to fix the error rates. Which brings us to Section 3, the fault tolerance challenge, conquering quantum noise. Here's the crucial point. Raw physical qubit counts, they are basically meaningless if you don't have fault tolerance. Quantum states are incredibly fragile. Just a tiny bit of microscopic interference, like stray heat or a random electromagnetic field, can cause a qubit to flip or completely lose its data. So you absolutely must have a way to actively detect and correct those inevitable errors during the computation process itself. Because if you can't correct the errors, you just can't run large-scale real-world computations. It's as simple as that. All right, Section 4, dual rail qubits explained, D-Wave's superconducting solution. D-Wave isn't just scaling raw physical qubits and crossing their fingers, hoping the problem solves itself. When looking at how to tackle this, CEO Dr. Alan Baratz put it perfectly. The industry has spent years talking about fault tolerance, but D-Wave actually has a highly differentiated and credible path to achieving it. They're pursuing a fundamentally different approach with their superconducting architecture, making sure they don't just compete, but potentially redefine what commercial viability even looks like. The real secret sauce here lies in error detection. Most of the industry relies on these really complex external fixes that require thousands of extra physical qubits just to kind of babysit the working qubits. But D-Wave's dual-rail qubits, they have built-in erasure detection. This native architecture catches an astonishing 90% of errors exactly as they happen. That real-time detection is an absolute game-changer. They literally spot the error at the single qubit level right in the middle of the computation. Because they catch these errors in real time, the results are just incredibly promising. D-Wave has demonstrated 99.9% fidelities on 2-qubit operations. That effectively means a physical error slips through the cracks maybe once in every 1,000 operations. By combining the crazy execution speed of superconductors with the kind of high fidelity usually only seen in trapped ion systems, they are fundamentally changing the math of quantum error correction. To really put this efficiency into perspective, we look at a metric called lambda. Now, lambda basically measures how rapidly a quantum computer's errors shrink as you add more error correction capability. Currently, the broader industry standard is a lambda value of around 2. That means each increment cuts errors by about half. But check this out. D-Wave's roadmap is targeting a lambda of 10. Every time they step up their error correction, errors drop 10-fold. It's a massive leap. It means they could hit true fault tolerance using significantly fewer physical qubits than their competitors, vastly accelerating their path to a commercial gate model system. Okay, Section 5, the roadmap to 2032, scaling to quantum utility. This is a meticulously planned multi-year engineering timeline. They're starting with just 17 physical qubits in 2026, mostly to prove the blueprint, but watch the acceleration. By 2028, as they scale up to 181 physical qubits, they're expecting a staggering 2,000-fold error reduction. That reduction is the key. It's what allows them to finally jump to logical qubits, which are essentially perfect, error-free qubits. They're aiming for a 10 logical qubit system by 2030, and then by 2032, a 100 logical qubit system capable of over 1 million operations. That 2032 milestone? That's when we start seeing those sci-fi, world-changing quantum chemistry and AI applications. And finally, Section 6, balancing today and tomorrow, the ultimate verdict. D-Wave uniquely straddles two worlds right now. They are the only dual-platform quantum computing company out there. They're generating actual real-world commercial revenue and providing 99.9% uptime with their annealing systems today, serving massive global enterprises. Simultaneously, they're taking those hard-earned lessons in superconducting technology and pouring them right into building an incredibly efficient, error-detecting gate model system for tomorrow. So what should you take away from all of this? Look, the current financial numbers absolutely demand a leap of faith if you're just staring at D-Wave's balance sheet today. But when you really zoom in on their dual-rail physics, those incredibly high fidelity rates, and that targeted lambda 10 efficiency, we really have to ask a much bigger question. Is surviving this current $32 million cash burn simply the necessary foundational price of entry for entirely redefining the future of computing? It's a high-stakes gamble on the very edge of modern physics, and we are going to be watching incredibly closely to see if their 2026 milestones prove this blueprint correct. Thanks so much for joining me for this explainer, and as always, keep questioning the data.